Okay, then let us start today.
Okay, sir.
How far you have come? Let me see. This is the sound today. Okay, so I think we have stopped here, right? Close or nothing. So I think we stopped here. Did you go through whatever we have derived in the last class? Okay. So this is what we are doing. We are finding the how did we start? We started after writing the writing the Hamiltonian for the electrons, electronic Hamiltonian within view approximation, right? And then uh, we have found the part of the Hamiltonian that is additively separable. This part is additively separable one, this one, and this one is that the problematic term for which we can't find a complete solution, right? So if we neglect this part, then we get a sum over in-body operators. Uh, so the function we are going to take is a set of one electron wave functions, right? Then we have defined the coordinate. This function we call as the spin orbitals. It has two parts. One is special part, that means xyz coordinate, and other is a spin coordinate, right? So xi will be a set of ri and omega I. And this follows the normal orthogonality relation, that is chi I chi j is delta ij. Right? This relation we explicitly put for the spin part, right? So when we write that chi I chi j equal to delta ij, it means that two spin function alpha beta they are orthogonal to each other. Right? So from there we have written a determinant. This is Hartree product. We have seen that Hartree product gives reasonable good result, but we have a problem. For electrons, it does not satisfy the exclusion principle, the anti-symmetry principle, which is if you interchange two electrons, the wave function must become negative. Okay, and that is satisfied by anti-symmetrous product or a determinant. If we make a determinant with the orthogonal spin orbital, that kind of determinant we call as the Slater determinant. So this is a Slater determinant. Right? We have done shorthand notation. You can write instead of determinant, instead of writing all the elements every time, you can just write the diagonal elements. Right? The chi I of x1, chi j of x2, and so on. You can also omit the x1, x2 coordinate by explicitly mentioning that the coordinate x1 will be for the orbital that is situated at the first, right? So chi I will have the coordinate xi. So with this, we want to implement the variation theory to get the ground state energy of any electronic problem, right? Whether it's any electronic atom or molecule does not matter, but we want to solve it variationally. Okay? And then we have written explicitly the expectation values, because what is variation theory? Variation theory is that if you take the minimum of expectation values of uh, Hamiltonian, this will be always greater than equal to 2 ground state values. So what we did, we take the approximate wave function constructed as a determinate from a set of spin orbital, and then we take the expectation values or average value of the electronic Hamiltonian. While doing so, we have now deriving terms by terms, right? We have taken two electronic problem, which will have the one electronic part of electron 1 and one electronic part of electron 2, and this two electronic part which will have the operator that will have the index for electron 1 and 2 together, R1, 1 by R1, right? And then we derive the formula or the expectation value of H1. Right? We found that it becomes just this term. We get only one term from H1, which is integration of chi I star x1 h1 chi I of x1. And then we go for the one electronic part of the second electron, that is H2. We also got the similar expression, that is chi I star x2 h2 chi I of x2, right? Dx2. So dx1, this will be dx2, right? So if we compactly write it, all the one electronic term will be just add the sum up. So if I have my original Hamiltonian, if you look at this, my original Hamiltonian will be H equal to sum of H of I equal to 1 to n plus sum over I, let me write it explicitly 1 by 2, sum over j 1 by 2 n, 1 to n, 1 upon I. So for two electrons, what I get for this term, I'll have H1 and H2, that will be equal to chi I star x1 h1 chi I x1 chi I x2 h2 chi of x2. So if I add them, I get sum over of I equal to 1 to 2. For n electron, it will be sum over I equal to 1 to n chi I star x1 hi chi. Let me write it x1 because they are same, and chi I of x1. Right? Basically, what it does, all the one electronic terms they add up. Now let us do for the two electronic part. What we are going to do here, for the two electron, right? This is 1 upon R1 R1 I sum over of I sum over. So what I'm going to do here is we are basically writing this term psi 0. Let us do only for two our two electron problem, that I have electron 1, electron 2, they are separated by a distance. So this is, right? Let us write it explicitly. What is chi I? What is psi 0? Psi 0 is this, right? 1 upon 2 factorial, not 1 upon root 2. Remember, we have written like this, chi I of x1, chi j of x2, right? 1, 2, is just writing determinant. Chi I of x1 I j of, and then for this also I have 1 by root 2. So basically I get 1 by root 2 into 1 by root 2. This will give me 1 by 2. Let us explicitly write this term. You will understand why we are doing this. This determinant, if we expand it, what we are going to get? We got something like this. Let us write the determinant. This is I of x1, I of x2, ij of x1, j of x2. If you expand this, what you get? The diagonal term, right? So I'll write like this. I get I of x1. Since the bra vector, I have to put a star here, and then chi j uh, uh, 2 minus I of x2 by j of x1. Everything will be start from the left side, and then I have 1 upon r1 2. Let us write right side. This half 1 by root we consume in this half. Let us write this same way. I have I of x1 I j of x2 minus I j of x1. This integration will go over dx1 and dx. Right? Anyone has problem with this up to this part? This has to be cleared very. This has to be extremely clarified. Right? Anyone has any issue? No. This part should be understood quite well, right? There should not be any doubt regarding this part. All we have done, we have explicitly written the determinant form, right, by as a functional form. This will be continuously shifting from one notation to another notation. Right? While doing the derivations, we'll be shifting from one notation to another notation, and you have to get used to it. Right? Don't stick yourself to one notation because it is convenient to use different notations and different time of the derivation. So this is the explicit. This is what we have done here. We have written explicitly the determinant in terms of the product, antisymmetric product function. Okay. Now let us write this. What we get here is of double integration. Every term must be multiplied with every term in the bra must be multiplied every term in the k. So what you get here, you see note down this one. This term must be multiplied with this operator. So let us write this. We have here. Let us put a bracket. This 2 is beyond the bracket within the common. So I have chi I of star x1 I j star of x2 1 upon r1 2, right? And then this guy I get chi I of x1 I j of x2 dx1 dx2. So this is the first term, right? This plus into this. Then I'm going to write this into this. So let us write that part also. I'll suggest you to do yourself. This is double integration of chi I star x1 I j star x2 1 upon r1 2. I get this. I get chi j of x1, chi I of x1. Right? So this is the second one. This multiplied by that. So I get this multiplied by this. Now I'll be doing this multiplied by the third term. So let us write that. Right? This, what did I do? This one multiplied by this one. So this should carry a negative sign. Then this one multiplied by this one. So that will also carry a negative sign. Double integration by I star x2 by j star x1 1 upon r1 to by I x1. Let's not confuse this. This is x I. I of x1 by j of x2 dx1 dx2. Right? And last term, this second and fourth, that both has negative, so I get a positive sign here. What I get here is I of x2 star I j of x1 1 upon r1 to I j of x1 2 dx1. Right? All term will come in as a negative. Right? So let us going to simplify this whole expression. I hope this part there's no doubt. If you have a doubt, please let me know before we move forward. There are four terms in the two electron integrals, right? We are talking about only two electrons, electron 1 and electron 2. Since they have two electron integrals, they can combine two spin orbitals. And we have four terms, right? Now look at this. The first one and the last one. There is similarity because between the first one and last one. What is I have? I have chi I 1 star chi I star x1. What I have here? Chi I x2. Look at this term and this term. Just give me a minute. So this is 2 or a term. I should get 4 terms, so I'm getting 4 terms. Let me write this. You consider the first one and the last one. There is something, am I missing something? Just give me a second. I hope not. Okay, let us do it, then let us see what we are going to get. Right? So if you inspect the first term and last term, what we get here, we have chi I x1. If you interchange this and this, if you have a dummy variable interchange, this is small, this is small. I'm just getting worried that shall I get the final version. Okay, let us do this. What we get here. You just do the dummy variable interchange. This will be equal to half for this term and this term, right? What we do here, you see, you have, if I make I equal to j, right? So let me write the first term as it is. I have integration of I star x1 ij star x2 1 upon r1 2. The first two term will write as it is, and then I write like this: I star x1 j star x2 1 upon r1 2. I write ij of x1 I of x2 dx1 minus this will be equal to this. So what we're going to do here, we have chi of x1 instead of x1. I will write x2. So interchange this. Okay? If I write this, I have chi I of star instead of x2. We are going to write x1. Similarly, here chi j star instead of x1, I'm going to write x2. 1 upon r1 2. Same thing, chi I write as x2, chi j write as x1, dx1, dx2. Right? This will do the same thing plus integration of, I write chi I star of x1, chi j star of x2, 1 upon r1 2, chi j of x2, chi I of x1 dx1. Right? Let us see. Did you understand that point? This part? Anyone has any problem? Let me see your expression. Up to this part, does anybody has any problem from this step to this step? No? You will understand what I did here. Basically, we made x1, we replace or interchange here x1 into x2. Wherever you have x1, you made it x2, and wherever you have x2, you made it x1. Similarly, for this step, right? So from here, we use this, got this. Similarly, here we use this and got this. This is possible because we are integrating over x1 and x2. Since we are integrating, we are actually doing the continuous summation. x1 and x2 become dummy variables. It does not matter whether it's x1 or x2 once we integrate. Right? Last day we have discussed this. Now you see the this term, the term first term and the fourth term, they're exactly same. I have chi I star x1, chi j star x2. I have chi I star x1, chi j star x2. I have 1 upon r1 to chi I x1. I have chi I x1. I have chi j x2. I have chi j x2. So this and this are exactly same. Similarly, this and these are also same. So I can write it as half double integration. We have chi I of x1, chi j of x2, 1 by r1 2. You should write 2 into, right? I of x1, I j of x2 into x1, right? And then I have minus I of x1, I j of x2, 1 upon r1 2. I have chi j of x1, chi I of x2 x1, right? So these two terms will combine give me this, and first and last term will combine give me this. So they also have this 2 will get cancelled. What are we going to get here is integration of x star x1 by j star x2, 1 upon r1 2 minus, right? Well, this is the final form we got. Okay, now you note down this the term here. Let us note down this one. You see, left side in the both terms they are identical. The right side, what is here? We have chi I x1, chi j x2. In the next, what we get here, instead of chi I x1, I get chi j x1. Instead of chi j x2, I get chi I x2. So if you notice this, in the right side, x1 and x2, they interchange their orbitals. Right? They exchange orbital. Left side, that's same. Right side, we have orbital interchange, right? So this term is called a Coulomb integral. This is called exchange integral. In short, we write again, we could introduce some shorthand notation. We write this whole as, in terms of bracket, we write as whole as chi I x1 chi j x2. This r1 by 1 by r1 we don't write, we just put one vertical line. So this line represents 1 upon r1, right? Right side I have chi I x1, chi j x2. This is the first term. The second term we write as minus, same way, chi I of, I'm sorry, we need to write star there if you're writing bracket notation. I have chi I of x1, chi j of x2. Again, this is just one vertical lines represent 1 upon r12. 1 upon r12 is there. So I write chi j of x2 chi I of x2. This is a notation, right? This also can be written in shorthand, just chi I, chi j, chi I minus chi I, chi j, chi j, right? These are shorthand notations. Sometimes it's also written as just like I j, I j minus I j, j. They have same meaning. We use lot of shorthand to uh, make the derivation easier, right? So that's the difference. There's no, I mean, in physics there's no difference. There's just different type, different way to write. So basically, this represent a double integration of chi I one star chi j one two, 1 upon r one to chi I one, chi I x one, chi j x two. The right side we have the interchange of functions, right? So left side you have ij minus ij. When we have ij ji, you get a negative sign. This negative sign comes from exchange. Right? There is no classical interpretation for this. There is no classical meaning for this. Why to get exchange? But there is a quantum reason. It comes from the quantum mechanics. It comes from the fact that electrons are fermions. Electrons, when you interchange their position, they change sign. Right? So this way of writing the expectation value is also called as a Dirac notation or physicist notation. So Dirac notation or physicist notation. Another way to write this, you see, let us uh, have that. You see what I have written here? Chi I star chi j. Right? In the chemist notation, this also written as one index, one coordinate left side and other coordinate right side. You can see, you can write this thing as a whole. Let me write this R12, right? Chi I star x1, chi j star x2, chi I x1, chi j x2, dx1 dx2 minus this become chi j of x1 chi I of x2 dx1 dx2. You see, this you can also think this way that I have for coordinate x1 chi I, right? We start and without star for x1 coordinate chi I. So this is written as chi I chi I. Right? It represents both as one coordinate. And then we have this and this as another coordinate. So I write chi j chi. This usually this is written in terms of a square bracket minus, if I follow the notation, what notation I am following? The notation I am following is that with the function that has same coordinate you write together, right? So what I'm writing here, I should write here. You see the function I have same coordinate is xi and xj. So this will be chi I, chi j, that is have coordinate 1, and for coordinate 2, chi j, chi I. So I write chi j, chi I. This also in short I can write I j, I, and I'm sorry, this is not correct. This in short I should write as I, j, j minus I, j, j. Okay? You see, this and this are exactly same. They are same equation but different way of writing. This is known as a chemist notation or molecular notation. Right? Just a writing. Why they use that is helpful for programming. Anyway, we're not going to do the programming, so for you it's not really necessary to know what is the difference between this. But basically, they are different way of writing the same equation. Okay. We can see that we can also write the same expression in the following way. This expression I can also write in the following way. I can write the whole thing as left side I have same, right? So I can write double integration of chi I star x1 by j star x2, right? 1 upon r1 2. I write as 1 minus p12, what p12 means, p12 by I x1. This is again another way of writing. What it does, you see, chi I j this term and this term with 1 upon r2 with 1 with this exactly becomes this. What this will do, this is an operator p12 is called permutation operator. What it does, it will exchange I x1 into x2. So right side, whatever wherever you have x1, it will make it x2. Wherever you have x2, it will make it x1. If that is the case, you see left side is exactly same as here. And right side, I have chi I x2, which is this, chi j x1, which is this. So this is another way to write the two electron integers. Right? So you can follow any one of them. I can follow the Dirac notation or physics notation. You can follow the chemist notation. You can also follow the explicit way to write them as integer. While doing this lecture, I'll follow all of them so that you should not get confused. Right? You should get used to it. Okay. This is needed. So in books and all, sometimes you may face a different type of notation. You should not get confused. Okay. Get used to it. Remember that whenever is the Dirac notation, I have all conjugate left side and without conjugate right side. Whenever molecular notation, I have first x1 left side and x2 right side. Right? And this is easier. This is just an explicit way to write them in terms of integer. Right? So this is all we got. Now this is for one electron, two electron integrals. If I write the whole thing, so for this is for only two electrons. If I have n number of electrons, that will become, so let us write this in this way. So therefore I can write E0 equal to, this is for 2. If I have n, you have to sum over of n, right? So I can write this as sum over of I equal to 1 to n. For one electronic part, I'll write Dirac notation. I have h I of h1 I, right? This last class we have derived this, and this we are going to make as 1 by 2 sum over of I, sum over of j. I have I is a minus I j, right? This is a Coulomb term, this is the exchange term. Right? As I said, we can also write in other notation n for one electron. Mulliken notation and Dirac notations are same. Like h, this can be written as sum over of I, sum over of j. Remember, I am putting half here, so I am not putting j less than I or I less than j. This will become I j j minus I j. And then you can also write in the explicit form sum over I equal to 1 to n intuition of I x1 h1 I of x1 dx1 of sum over I sum over j. We have right minus dx1 dx2 minus I star x1 I j star x2 1 upon r1 2 by j x1 I x2. Right? Now this is the whole expression in terms of spin coordinate. Right? We have to optimize this using variation theory. You have to optimize this E0 with respect to chi's. Chi's are the spin orbitals. These are the variation parameters. Okay? So we have to optimize that in terms of chi I. So how to do the optimization? Optimization is the process where you make first derivative equal to 0. Right? If you remember the optimization, the stationary point, finding stationary point in mathematics. If I have y equal to f of x for the minima or maxima or saddle point, then f prime x equal to dy dx equal to 0. So from that we get the equation of y, right? If you solve this equation, you find different point of x. On those points, some will have maximum value of function, some will have minimum value of function, some may be neither maximum nor minimum but change of the slope. Okay, and for the to confirm that is minima, what we have if double prime x is greater than 0, it's a minima for a minima, and if double prime x less than 0 for a maximum. Am I correct or am I wrong? For minima, it is less than 0, right? Or greater than 0. Any response? For minima it is greater than 0, right? For maxima it is less than 0. Okay. So we have to minimize this with respect to set of orbitals. What we have here, minimize E0 with respect to set of chi I. You see, chi I is not one, there are many. So with respect to set of chi I, you are going to minimize it. How are you going to do that? So basically what we are going to find as delta E equal to 0, right? But there is a problem. Problem is that the chi i's have constant. You see, if you remember the minimization process, what we do, let's say I have fx equal to x square, and write it, uh, use some other color. So what we have here for minimization process, let me write it separately. For a minimization process, let's say I have y equal to 5x cube. How do you do the derivative? You put dy dx, you get as 15x square plus 2, right? And then let me put it minus here so that you encounter the complex root. So minus 2x. So I get minus 2. And then what you do, you put this equal to 0. So you get x square equal to 2 by 15, x equal to plus minus root over 2 by 15. That's how we do, right? That's how we do find the minimum. Take the first derivative and put the first derivative equal to 0. Find the value of x. You see, this is possible because x and y are independent. In the sense, if you plot this, you get x-axis, you get y-axis, and these two axes are perpendicular to each other. If you change x, you can change x independently of changing y. So these two are vectors; they are perpendicular. They do not depend on each other. However, for this case, I cannot just change chi I because the moment I get change chi I have this restriction chi I, chi j, this is equal to delta I j. I have this restriction. So even if you change chi I, you should change chi j such that the new chi I, new chi j are also orthogonal. So this is a constraint. In variation theory, we often encounter this problem where the variables are not independent, they are dependent. So if you have a dependent variable, there are many ways to solve this. Right? The most popular way is called Lagrangian multiplier. What we are going to adopt here is called Lagrangian undetermined. Right? It is also called Lagrange variation theory. There are many. There are Maclaurin variation theory. There are some other. Okay? So what you do here, you see, we cannot minimize this with respect to chi I because they are orthogonal. There's a constant there. What we'll do, we have a form a new function, let's say lambda Lagrangian, which is also a function of chi I. And then what we're going to do here, we write this E0, which is a function of chi I, and then this is a constant, right? So I can easily write this constant in terms of equation. I can write delta ij minus chi ij equal to 0. So what we do here, we put this writing it this way, doesn't matter. I have, should not be negative, I have minus delta ij equal to 0. So what we do here, we put this as a constraint I minus delta ij, right, equal to 0. Now, if I can, this itself is 0, right? So what I can do, I can multiply this whole thing by another constraint, let's say epsilon ij, right? So that is equal to 0. For which I and which j? For all I and all j. If I have n number of I, n number of j, for each I and j, this term equal to 0. So I have multiplied this term with another constant, right? Epsilon ij. So epsilon ij is the multiplier. And this is the procedure. You have done this when you have done the statistical thermodynamics, right? In the Boltzmann distribution. All we need to do is, instead of minimizing this guy, I have to minimize this. Right? So all we need to do is find delta lambda equal to, that's all, right? And this is little bit tricky and time consuming. We have to do term by term. So we have the expression for this. We have the expression for this. Of course, this is either 0 or 1. The derivative of that is 0. Right? The derivative of constant is 0. So we have to derive this. So basically this is 0. So what I have to do? We have to find delta E 0 I minus delta sum over of ij epsilon ij. This has to be 0. So we have to derive each and every terms, right? So let us write this. This, if you remember what we got here, we have delta of one electronic part sum over I I H I. We have two electronic part of Ij 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 minus Ij, right? This is all this E, and then you make this sum over Ij. This is a constant epsilon Ij, it's multiplier. I have delta of this. Do this. This implies you have to do this separately for each and individual terms. Let us write them as labeled. So let us call this number one term. This we will call as second term, third, and fourth. This we don't need to do because that's a constant. We take the derivative, it will become automatically zero. Right? You have to do each and every term separately. So let us just do only one today, and Thursday will complete the other terms, right? We'll start from the simplest one. So fourth term. What we get here? Sum over Ij This is your double sum epsilon ij. You take derivative of the left side, the bra vector. If you take that, you get delta of chi I chi j, right? Then you take the kth vector. I mean, yeah, you take the kth vector, then it becomes chi I delta ij, right? Now you see these are integration, right? So you can write like this sum over ij epsilon ij. Let us write in terms of integration. I have delta chi I star chi j d. I have to write the coordinate. So we have here epsilon ij delta integration of delta chi I star x1 chi j x1. These are just overlap, orthogonality overlap. So I have only one. I get from here chi I of x1 star delta chi j of x1 right? Now you can see that I can just do my exchange of variables, right? Since they are dummy variables, since I have integrated over all I and j and all x, I can make I into j, right? Because I have sum over it. So you can write this as sum over ij epsilon ij. You make it as delta chi I star x1 chi j x1 dx1. What we do here is just make chi I of chi j of x1 delta chi I of. Now look at this. This here chi I star, here delta chi I star, here delta chi is without star. Here chi j is without star, here chi j is with star. So this basically complex conjugate of this. If you take complex conjugate of this, conjugate become without conjugate, I get delta chi I, which is this. I get chi j as conjugate. So I can write this is equal to ij epsilon ij integration of delta chi I star x1 chi j of x1 dx1 right? So all the last term that is going to give us the final expression equal to sum over I j epsilon I j chi I, right? That's all you get. So this is the fourth term. I'll stop today. Next class we will do the first term, second term, and third term. I will suggest you to try at least the one body terms you must try. Okay. Left side first do the derivative of the bra vector and then derivative of the ket vector. You will find that one term will be conjugate to another. Right? Just like this. One become conjugate to another. This here also you get one is conjugate to another. That's all you're going to get. This two will do in the next class. So I suggest you to do this, expand this as homework. So what I'm to do this delta of I h